Okay. Hello, everyone. Good morning, good afternoon, and good evening, everyone. Thank you for joining us today in our session, linking live session on embracing geological complexity in open pit mining design from Leapfrog to GeoStudio. So today we have with us Mr. Sing Chen. He's our Senior Product Success Manager, our expert in this topic, and he'll be sharing more with us later in this in the technical demonstration session. And my name, I am Jamie. I'm the product sales engineer for our geotechnical solution in Southeast Asia region. So without further ado, let's get started. I will first start off with introduction to Bentley Geotechnical Engineering Solutions. Then we'll move on to the demonstration by Sington, and then we'll run through some brief you through Virtuoso Practitioner License, and the Q&A session will be at the end of today's session. So if you have any questions throughout Sington's presentation later, feel free to write them down in the comment section, and then he will be addressing your questions at the end of today's session. So for Bentley Geotechnical Engineering Solutions, it comes in three main categories: geotechnical information management, geotechnical modeling, and geotechnical analysis. For geotechnical information management is for subsurface data management and reporting purpose. So we have open ground, GIN, and kinetics. GIN and kinetics are undergoing progressive retirement right now. So if you have any need for geotechnical information management solution, Open Ground will be the solution for you to go look into. For geotechnical modeling, we have Leapfrog Works, which is used for you to model and visualize your subsurface condition so that you can make better decisions in your project. And for geotechnical analysis, we have Plexis and GeoStudio. Plexis as our finite element geotechnical analysis software, GeoStudio for equilibrium slope stability analysis. And today our focus is on GeoStudio. This slide here shows like a general workflow of geotechnical work in your project. So for geotechnical work, we always start with site study or site investigation work. So this is when Open Ground comes into the picture, where you can use it to consolidate and manage all the subsurface data that you have in your project. And then all this information can be pushed into geological or subsurface modeling by done with Leapfrog Works. And with all this information that you have, you can then push the information for subsequent geotechnical analysis, either with Plexis or GeoStudio. And since today our focus will be on GeoStudio, I'm just going to share briefly on GeoStudio solutions. For GeoStudio, we have GeoStudio 2D, 3D, and GeoStudio Flow. For 2D, it comes in 3 product tiers, and for 3D, 2 product tiers. And for GeoStudio Flow, it comes in 2D and 3D. So between GeoStudio, for GeoStudio 2D and GeoStudio 3D, the difference between the product tiers from base, advanced, and ultimate is the same. So if you require only very fundamental or limit equilibrium slope stability analysis, the base tier will be sufficient for you. And if you require any groundwater analysis in your assessment, then you will need at least the advanced tier. And for the ultimate tier, it includes stress-based stability analysis as well. And for GeoStudio Flow, this is an all-in-one tool for transfer processes, more for geo-environmental project analysis. You can use this to model environmental protection work, groundwater flow, groundwater freezing problems, and it comes in 2D and 3D. So without further ado, I'm going to hand over the session to Sington. So over to you, Sington.
Yeah, sure, Jamie.
Thank you.
Right. So, good morning, good afternoon, which might be the case. Sinchen. So, in this session, we're going to review the effect of geological structures on the stability of an open pit mine using Slope 3D in GeoStudio. So, the design of engineering structure in large rock masses often requires the consideration of structural geology at a variety of scales. Structural features such as fault, and discontinuities controls rock mass behavior, and therefore contribute to either stabilization or destabilization of the rock slope. So in this session, we'll review the Leapfrog interoperability with GeoStudio by first examine a geological model in Leapfrog work and then bring it in directly into GeoStudio for the use with Slope 3D. We'll also spend some time, defining a background mesh using the concept of construction plans. And then we'll use these background meshes to come up with a definition of which surfaces that represents the geological structures. And finally, we'll see what the effect of these faults are on the calculated factor of safety and also the mode of failure, or what I call it the critical mode of failure for this open pit mining problem. So there are several factors, that controls the stability of the slopes in the rock masses in a manner as natural, hill slopes. So first, groundwater flow and bore pressure are often critical. And uncertainties in geological model can also be very important, especially given the complex geological systems found in many open pit operations. Some scenarios, the stress strength, constitutive behavior of the rock mass must also be considered. And in terms of in situ stress conditions, so gravitational stresses generally govern, but there are also scenarios whereby the high area of horizontal stresses can actually lead to some problems. And then we have the dynamic loading due to seismic events or even microseismic events, which can equally, lead to weakening of rock and therefore controlled stability. The mechanisms discussed in these last three bullet points generally require a finite element approach using Placis 3D. And finally, the most important in the context of this presentation, we have geological structure including joints, faults, and beddings. The structure determines the complexity of failure mechanism, which could range from translational to a more complex, multi-mechanism, the kind of failure. So let's consider the case shown here. Taken from a paper by Stat and Walder 2015 from the Journal of Structural Geology. From the first pan, we have a planar translational mode of failure that's apparently, controlled by a joint set dipping to the right. And in the second pan, all right, there's a single set of bedding also dipping towards the right. But in this case, we have a fault that creates a release, sort of a release surface that allows the wedge to actually move laterally to the right. And finally, we have a complex bedding system, involving steps and undulations that leads to an irregular compound of sliding mechanism. And in order to consider this in three-dimensional limit equilibrium analysis, we must use the concept of wedge surfaces in order to create a slip surface shape that is commensurate with the failure mechanism at hand. And with the background information stated already, so today we'll review a throat 3D analysis of an open pit where the geology comprises, 10 stratigraphic unit. All right, so the strength definition of rock is irrelevant for this discussion, but I'll note that we use a Hoop-Brown model to actually define the shear strength. And what makes this case more interesting is that we have two faults identified over the north and northeast of the pit wall. There is also gouge material within these faults that comes with a friction angle of 14 degrees and a cohesion of 0 kilopascal. So we'll investigate three scenarios to explore the effect of combining, all these faults to produce the final sliding mass. And of course, in the base case, we actually exclude all faults. And case two, we explore the effect of activating each fault individually, while the final case reveals the impact of both faults, being active simultaneously. All right, so Sequent had laid out a geotechnical workflow to address the challenges coming from underground. We have a connected ecosystem that typically begins from open ground through leapfrog work and ultimately geotechnical analysis solution of GeoStudio and Placis. So in this session, we'll focus on the leapfrog work and GeoStudio. So with leapfrog work, we can take the factual data direct from the source and combine it with a broad range of other site information, geoscience, and engineering data to create an engineering geological model for your site. So Leapfrog work is a dynamic, combining input data and user interpretation together in what is arguably the fastest and also most intuitive geological modeling process. The fast and iterative modeling approach combines with sequence central model management capability, audit trail, and collaboration tool to develop and communicate understanding, even in complex and dispersed or cross-company project teams. And then finally, typically the last piece of the geotechnical connector workflow is to do the actual analysis. To validate your geotechnical design, to evaluate the performance of geostructures, as you construct and operate. And that brings us to the representative solution of Placis and GeoStudio. So Placis is an FEM finite element method based solution for geotechnical deformation and stability analysis. And GeoStudio, on the other hand, is LEM, limit equilibrium based method. Designed for calculating the factor of safety or probability of unsatisfactory performance. It's meant for slope stability analysis by means of slices and the newer stress-based method. So again, we going to kind of stepping through just this workflow, between Leapfrog work and GeoStudio. So now let's start with a brief review of the geological model in Leapfrog work. So you're in Leapfrog work, by the way. So in Leapfrog, you can sort of generate a geological model using a variety of data. So generally speaking, we begin with the topographic surfaces, just like this. And in case we have already brought in the model space showing an open pit mine here. All right, at a certain snapshot in time. So with the topography in place, we can then go into the model and add borehole data, design surfaces, points, and polylines, or those features. So if we had a control session, we could actually include it here in the model space. You can sketch polylines on the sessions and use those kind of a geometry to inform the geological model. And on top of that, we can also bring in, geophysical data, structural data meshes. So with this model, once we have completed it, we actually produce our geological model as shown here. And over the project tree, we see the various output volumes just for this model. So as mentioned, so there are 10 geological units, all together in this model. So if I were to actually throw in one of the surfaces, which is here, so intrusion surfaces, and I hide partially our model, so you can see there's a fairly big surfaces, intrusion surfaces. So it's this is how we can actually create surfaces. To create an intrusion through the geology types. All right, that actually intersect with our major geological volume already in the model space. So it can be very informative also if you can use the slice tool to actually slice through the models. Right, so first we get the top view. So this is the slice tool. Can actually activate from top surfaces. I'm gonna cut somewhere around here. Right, so you can actually look at the arbitrary cross-section and its geological, volumes and everything. So you can actually go into the center of the models. So this is somewhere from the center. So if we do again, gonna do this, right. Okay, you can sort of fly through the entire model space just to look at the variation of your underground soil profile. So in this, quite informative if you have this kind of interactive tool. So what's like live cross-section. It's very useful to inspect the final product. And on top of that, we can also create a number of cross-sections out of 3D or out of this 3D geological model. So we can have, you can also do this kind of, section cut. And you can actually export all these sections over to GeoStudio, Slope W for 2D slope stability analysis. So you can actually export, you're open to option to actually export all these objects. So these are, a few supported format. So it comes in terms of .dsf, DWG, DGN, and IFC. So these are all sort of exportable. So you can choose to actually export and import into GeoStudio for 3D, equilibrium analysis. Yeah, so this is it. So we're about to move on to GeoStudio, right, for slope stability demonstrations. So here we have an import option. So you can choose to import background mesh either from file or from the central. So central is centralized platform actually manage all this geological data. All right, so in this case, you can actually either go for import from file. So a list of a supported format could be DSF, DWG. And if you go to the geological volume import options, so you have the OBJ, support the kind of format supported. So in this case, we're going to import by the central. So I have already signed it in to the central server. So I'm going to choose the server. Just take a while. All right, I'm going to select this project that's already been published over the central server. I'm going to look at the sections. All right. All right, there you go. So down there, down at the bottom right, we see the status bar from the, for the import of the volumes. It might take a while, so since this is a very heavy model. All right. So once the import finishes, we see that the geological model is not actually oriented in line with our Cartesian axis system. So in this case, the z-axis is up, is pointed up and down in Leapfrog, whereas the y-axis is up in GeoStudio. So the first thing I'm going to do here immediately after the import is to actually try to remap the axis system for some consistency. So in this case, all right, so our x remain as x. So y, I'll switch to minus z, and z, I'll switch to minus y. All right, so note that the model domain is actually quite far away from the origin. So it's a good model in practice, whether finite element or limit equilibrium, to keep the model domain close enough to the origin of our Cartesian axis system or origin. So to do this, I'll simply hit the button to adjust the base point. All right, so once we have done that, we just click OK. And also to save the transformation template. So again, down the bottom right, we see the final import of geological models with the geological model already in place. So almost there, 70%. All right, so there you go. So with this geological model here, if we look at the model explorer and under the drop-down menu, all right, so you can see actually we actually import those geological volumes. So we have 10 units as mentioned earlier. So it's all been bracketed. All right, so this model are actually dynamically connected. So let's say for the case when geologists was to go and update the model in Leapfrog work and try to publish it to the central server, and all I need is to right click on this button to reload the model inside GeoStudio to pick up whichever, new settings or new changes that has been done by the geologists. So the model will be, updated automatically. So with the import of these models, we also get the import of all the material. Also got the import of all the material here. And also they receive their respective colors just to differentiate, amongst themselves. All right, so then from the define model manuals, I can go into, I can choose any of the model and make changes on the material properties. So as mentioned, I use the hook brown models to represent the materials. Right, so these are the properties. So next we're going to, draw the slip surface limit. To define the extent of our slip surfaces. So in this case, I need to reorient the model. All right. Right, go to define slip surface limit. Right, then I'm going to use the mouse click to actually define such a search zone. Add. All right, so I drop a point here. I'm gonna connect this somewhere around here. And right click to close. So this is how we actually defined. So moving over to the model space. So this is the extent of our search zone. So in this case, we use the cuckoo search method. So in this case, from the define project menu, you're going to add a slope 3D analysis. All right, I already have it here. So slip surface type, leave it as ellipsoid, and the slip surface option go for cuckoo search. Define number of iterations, number of nest. Right, so this is how we're going to come up with the definition of yeah. So we're going to name it as the base case with no fault in place. Then we're going to clone it and rename it as a case number B, where we introduce fault number 1 with rest of the setting, identical. So fault number 1. So next we're going to define some construction plan. So in this case, I'll look at the plan button, which is here, right? I'm going to rename it. This will be fault 1. And construction type, we're open to various options. So in this case, we go for the plan from deep directions and deep angle. So in this case, okay, then the XYZ coordinates as the reference point. All right, and deep direction will be 250, deep angle 30. So remember when we first brought the geological model into GeoStudio, the first thing we did is to remap the axis. And there's another key piece of data. It's actually the base point right there. So now the base point, when we first bring it in, is the furthest extent of that model domain. So once we remap the axis and adjust the base point, so everything got shifted over and change its orientation. All right, so we need to actually take this into account when come up with the input of plan position in terms of the XYZ coordinate. All right, so once we see the intersection point for the symbol showing up there, all right, so that's about to move up. So click OK. So this is the fault. So likewise, we're going to do the same for fault number 2. We're going to use the same options from deep directions and deep angle. So this time around, we have a different set of XYZ coordinate. Just for fault number 2. So it will be 196 and 37. All right, so this is how we actually introduce the two fault through the plan grid or plan options. So now these are just construction plans. So I can actually right click on one of and any of these plant. All right, and actually to convert into a background mesh. So there's various way to do so. You can find from the menu. So first we look at fault number one, and we're going to rename it to fault one. All right, so now you can see. So we have to generate a background mesh out of the fault number one, the plan that representing fault number one. So by converting, alternatively, you can also choose to import such a plan as a background mesh. All right, so there's various ways, there are various ways to actually achieve the same goal. I mean, so in order for slope 3D to create something like piezometric surfaces or which surface, I mean, those kind of features, so we actually need this kind of background mesh. So once we have it, so we need to repeat the same step also for fault number two. So likewise, I'm going to choose it, highlight it from the Model Explorer, and going to hit the button to just convert it into a background mesh. In this case, I'll rename it to fault number two and hit OK. All right, so this is how we can introduce the background mesh representing the fault. Right, so I'm going to tune down the visibility a little for better clarity. All right, so there we go. So once you have the background mesh in place, so the next thing you do is to create a width layer. So you are working in case number two, so it's a fault one. All right, with just fault one active. So I therefore navigate to define which surface. All right, I'm going to add a background mesh that representing fault number one. And down here, I'm going to click on the button to choose the correct material type that representing the which surfaces. So once you see the color change, that means the setting has been done correctly. So now the material has been, correctly, associated with this particular weight plan for number one. So in this case, we're going to go again at the define project. And once again, we're going to clone another phase. So in this case, we'll rename it to case number C. And in this case, we have only fault 2 active. So likewise, we're going to go to some settings, define which services. In this case, we'll add fault number 2. Choose the corresponding material. And finally, the last case where we'll consider the two faults actually adding together. So likewise, clone case number D, we name it to fault 1 and 2. So in this case, we need to define which are the active wedge surfaces. So we need to actually add two background mesh. All right, so there you go. So this is how we finish the setup of models, and materials. So once we have imported from Leapfrog work. So this is how to actually translate into analytical models that's ready for analysis in GeoStudio. So about the weak surfaces, so what's going to happen? So some of you might have the question, what's going to happen? I mean, when the slip surfaces get introduced into the geological models. So this is how it works. So if it intersects fault number one, the ellipsoid will actually be truncated, and you will therefore follow the weight layers. And then whenever it intersects with the ellipsoid again, it will re-emerge near the toe. So this is how the stability, I mean the stability is being structurally controlled. So we'll see that more clear, I mean, when we go to the results. All right, so next I'm going to look at the results. So let me see which surface. So I have. So I mean, at this point, we have finished the generation of the geometry. So material has been defined, and we have added which surfaces were appropriate. I mean, for each cases, you have the corresponding, I mean, background mesh for either fault one or fault two or their combination active. So next step is to generate a mesh. We're gonna hit this button. So we have two options. You can actually, I mean, mesh a geological models volume, which is what we're doing right now, or to mesh parametric geometry. So parametric geometry is what you actually import, I mean, from, I mean, the parties. All right, so in this file, we only have the geological volume here. So that's our option by default. And the first mesh option is for the geological model volume. And that's what allows us to visualize the contour and data on the domain. So now we see that the current mesh is very coarse. I mean, because with the parameter defined is quite large. So in this case, I will change it to some lower values for better mesh refinement. And down at the bottom of this dialog, all right, so is the slope 3D column mesh settings. So we have option to actually generate tetrahedral or hexahedral elements. So in this case, we go for tetrahedral. So in this case, I'm going to tune down the column spacing from default to 5 meters. I'm going to hit the button to generate. The bar is moving. It's pretty fast. All right, so when you are landed in the mesh mode, you can actually switch on the top surfaces. All right, so and with this button active, the column, so it allows us to actually inspect the density of column grid. So by using the 5-meter setting for the column grid, and when we look from top down, we see that there's a very, I would say, adequate level of discretization already. I mean, given our topography and the scale of our geometry. So I would say this is a good, I mean, very good settings for these problems. So it's a good practice to use a decent size, not overly fine, and then refine later on, just to see if there's any effects on the calculated, I mean, factor of safety. So as you might know, because this result could be quite mesh dependent. So let's look at the result. So first, we're going to look at the base case that's without any fault in the model. All right. So we see that the factor of safety for the critical slip surfaces is around 3. So this is when there's no fault, I mean, present in the models. So notice over the left-hand side, just like in slope W. So we can click and drill down the list to select different slip surface. And from the slip surface docking window, I can also toggle this button, auto select critical. And this takes us back to the slip surface with the lowest factor of safety in the draw contours of the menu bar. All right, so there's a draw contour button here. The draw contours, the first tab is applies to the entire domain, and we have the second tab actually applies to the columns. So you can actually draw contours either on the entire model domain or on the columns. So from the contours, so as the name suggests, so we have by default already some contour generated. So the pore pressure in the sliding mass or the effective normal stresses that is reported on the columns. So you can actually, by selecting any entries from the list, you can actually look at, we can visualize our results just like that. So let's go to the draw graph window. All right, so the first one we're going to look at is the factor of safety versus sliding directions. So in this case, we can see that a critical factor of safety is around 3 and has a sliding directions is like 205 degrees. All right, so let's look at the lambda. This is for convergence. So lambda, I mean the safety factor versus lambda x. All right, so just like in 2D Morgenstern price analysis, where we have to search for lambda to make the moment and force factor of safety the same. So it's equivalent in 2D, I mean in 3D. So except for we have to actually search for both in the x and z directions, because now you're working in a three-dimensional space. So there are two axes actually define your horizontal plane. So this is the additional check for convergence when it comes to 3D modeling. So in this case, we also look at the FOS in another dimension, z-axis. So both the factor of safety, I mean, suggest that there's fairly good convergence. And finally, we have the plot of friction angle. All right, friction angles at the base of each column, so we can actually toggle, I mean, all these buttons. And then we have the normal stresses. So for columns, you can look at in the x direction and the z directions on the same plane. So these are the normal stresses at the base of each column along the z-axis. So we can also review the safety map. All right, so in this case, we can actually choose to display all the 900 trial surfaces. And this is how it looks like. So it gives us a good idea how the cuckoo algorithm search for the most critical slip surfaces. As given by our constraints, remember how we impose on the search by defining the S10 of search. All right, so that's why all the slip surfaces actually fall within the range that we have defined earlier. And our critical ones actually sit within this, within the domain. So next we're going to, I mean, for more clarity, we're going to hide the solid. So tune down the opacity, some lower values. All right, so in this case, all right, I think I just need to switch off all the irrelevant ones. So this is the base case without any fault. So I think you can actually have a better sense of the shape of the slip surfaces. They correspond to a factor of safety of 3. So this is the effective stress plot. So we have used, by the way, the ellipsoid slip surface shape. And in fact, I'm just going to turn this, so this is clearly an ellipsoidal shape as what we have defined already in the early stage, the define project, the first step. So this is how we get this kind of ellipsoidal slip failure. Yeah. So let's go to analysis B. So let me switch it back. So case number B. So this is the case with one fault number one active. All right, so you can see the factor of safety. With the fault one active actually changed from 3 to 1.5. All right, so notice that the mode of failure. All right, so if I could hide all this, better clarity. All right, if you look at the mode of failure, so and the location of slip, so we actually see the slip tends to move towards the east. All right, so there's a shift of this critical sliding mass, from the base case as compared to the base case. So now when we move on to case number B, all right, with one fault active, we see the sliding mass actually, shifted towards the east, all right, because of the presence of this fault number one. So we see fault one is dominant on this portion of the open pit. If we go back to the define, all right, so fault number one is here. All right, so this is fault number one. So this is how it actually intersect with the geological volumes. All right, so it actually set the tone of how our critical sliding mass is going to be like. All right, it's a planar translational slide over here. All right, so it's not surprising that it actually imposes an effect on the shape. So no longer we see this kind of ellipsoid, but I'll say it's a rather translational planar, the kind of failure surfaces. So next, if we go and look at the other plot for columns, gonna generate columns. So let's look at the maybe friction angle. So we're going to generate a plot on the columns. Look for the right categories. There's friction angle and going to show the legend. So clearly, so remember the friction angle for the wedge surface that we have defined is 14 degrees. So which is here. All right, the blue colors. So these are the friction angle at the base of this sliding mass, just in case B. So if you look at this kind of heat map, all right, so you actually get an idea of where the material is, what are the materials actually involved, in the entire sliding mass. So you can see that the columns right here in blue is apparently truncated by the weak layer that we have introduced as fault number one. So therefore, we have a reduced friction angle. So if you look at the legend, so there's 14 for the blue area. All right, let's switch it back on. A look at case number C. So in this case, case number C, case C, so we have a factor of safety goes up to 2 with fault 2 active. So this is fault 2. Fault 2 is somewhere here. All right, fault 2. This is how it intersect with our model. And once again, we go back to the result, and this gives a factor of safety as 2. So the critical surface actually now moved towards the west. So let's play it one more time. So this is the base case. For the base case, this is the slip. All right, then case case B with 1/4, so it shift towards the east. Then case C with 4 active, it actually shift a little back to the west. So notice at the meantime, the sliding mass is now much bigger than in the case of B and C. All right, so if we finally move to, all right, so let's look again at the columns. I mean, for this case number C with 4 2 active. All right, so clearly this is the location where it intersect with the weight surface plan fault number 2. So it's your planar, I mean, area. So with the blue indicates the friction angle of the wedge surfaces. So finally, we'll look at case number D. Switch it back. So case number D, we have introduced both fault 1, fault 2 acting together. And this gives us a factor of safety, I mean below 1. So and the critical sliding mass is now sitting somewhere in between the position of B and C. So this is B, take a while, okay, C, and now D, so it's somewhere in between. So once again, I mean, if we look at the contour for this case, and if we look at the friction angle plot, all right, so I mean, the friction contour friction angle on the columns for this case clearly demonstrate that with fault 1 and fault 2 active, they are controlling the shrink at the bottom of the sliding mesh. All right, so this is how you can get out of, I mean, various plot and graphs. And if I look at this FOS, factor of safety versus sliding directions, all right, so it's around, I mean, 209. So that's the sliding directions. So a lot of information is also available, right? So let's look at the slip surface shape for case number D. All right, so clearly when two plane adds together, so we get this kind of, I'll say biplanar or bilinear shape at the base. All right, with the material highlight as a blue, so there's the weak material color with a friction angle of 14 degrees. So this is the slip surface shape. And as mentioned, a lot of information is also available by this, the view sliding mass tool. In this case, we see factor of safety, the total volume involved, and the sliding directions of the mass of the slip. All right, center and all those geometry, I mean, information about all this slide mass is all reported here. All right, so let's go back to our presentation. All right, so in summary, three-dimensional stability analysis is often required to capture the effect of geological structures on the stability. And as you have seen, the structure determines the complexity of the failure mechanism, which could actually range from translational, as what we saw in this example, to complex multi-mechanism failure in the last case. All right, so this example also demonstrated that the weak sliding surface formed by the fault filled by the clay gouge has a significant effect on the calculated factor of safety and also the location of the critical slip surface. And the analysis explore, also the effect of activating each fault individually, and then we also combine it simultaneously And finally, given the topography of the site and the orientation of the faults, one of the two faults had a dominant effect on the critical mode of failure, so it's evident from one of the cases. So with this last frame, I'll conclude our presentation. So I'll turn it over to the host.
Okay, thank you so much, Sing Chen. Allow me to share my screen again. So yeah, thank you very much, Sing Chen. And I hope all of you, ladies and gentlemen, that you find this session useful for you as well. So if you have any questions, please feel free to drop them in the comments panel and we will answer them shortly. So while waiting for all of you to put in your questions, and also if there's any that Singson will read through them, allow me to share some information with you. Since this is about mining project and about between the usage of Leapfrog and GeoStudio, this is a success story of our user that we would like to share with you. This is from the Emperatriz project in Peru, where they were developing lithological and structural modeling of the mining project. This will allow them to improve their prediction of the rock quality and subsequently contribute to their worker safety and reduce cost and operational risk of the mine as well. So by using Leapfrog, GeoStudio, Central, and Oasis Montage, they get to improve their design workflow and reduce model delivery time and resources by 50%. And the modeling time was reduced significantly as well. So for this success story, I'm going to share here a link in our comments panel as well so that you can take a look at this short article on this success story. Okay, I've put this in here already. So up next, I'm just going to run through briefly on Virtuoso Practitioner License. Virtuoso is our Bentley e-store where we offer you a way to purchase our license at a more affordable price, and it comes bundled with free trainings and expert services as well. So for Virtuoso subscription, since it's on our e-commerce platform, it can be purchased by any entity, whether you are an individual or you come from an organization, be it a small one or a very large one, you can always purchase a Virtuoso subscription from our e-store. And this subscription is also flexible. Why? Because it's a 12-month subscription. So there is no commitment for you to continuously renew the subscription if your project has ended. And on top of that, with the subscription that you purchase, it comes bundled with this item called keys. So keys are like tokens or credits that you can use to redeem free customizable training for you and your team. So how does it work? When you purchase a GeoStudio Virtuoso subscription at our e-store, the purchase comes bundled with keys. And with these keys, you can unlock different types of training. All these are online training done through Microsoft Teams. It can be a tailor-made training program, which means that if you require training on a certain topic or certain type of analysis of that using that software, you can highlight it to our technical team and they will be able to advise you accordingly on the training that suits this requirement of yours. And it can also be an on-demand training or recorded training. We have trainings that are already available where you can view it at your convenience, at your own time and pace for a period of 90 days. So if this method suits you better, then you can always redeem the training, the recorded training, and watch it at your own time. And we also have mentoring services where the content is based on the specific requirement that you have for your project. The number of keys, they vary, not varies depending on the product that you purchase. So for GeoStudio, all GeoStudio licenses, GeoStudio 2D, the lowest, the base tier of GeoStudio 2D, it comes with one key per license. As for the rest of the GeoStudio tiers, in 2D, 3D, and Flow, each license comes with two keys. One key is almost 2 hours of training. So, in summary, Virtuoso is a practitioner license, name user license that can be reassigned, and this is a yearly investment without any additional maintenance to pay. So, with this, you will have full control over your yearly software costs, and throughout your whole active subscription period, you get to have the benefit of free technical support assistance, free software updates or upgrades. If there's any new releases, you can download them for free, and also, as explained just now, you can redeem the expert services or trainings using keys. And if you happen to have a requirement for both finite element and limit equilibrium analysis, our eStore also offer this solution called Geotechnical Analysis Worksuite, which is a bundle of both Plexis and GeoStudio. So for the Geotechnical Analysis Worksuite 2D, it comes with the highest product tier of both products, Plexis 2D Ultimate and GeoStudio 2D Ultimate. And for Geotechnical Analysis 3D, it comes with the highest product tier as well for both solutions, Plexis 3D Ultimate and GeoStudio 3D Advanced. So if you have any questions, just feel free to let us know, and we can address your concerns accordingly as well. So up next, we move to the Q&A session. We have not received any at the comment section yet. So we're just going to wait for a while more. If there's no further question, then we can move on to the next portion of this event. All right. Since there's no question, I think we'll move on to the last part of today's session.
Yeah,
And if you
sure, Jamie. Yep.
Okay, thank you very much, Vincent. So after this, if you have any, for those who are watching the recording, if you have any question, feel free to reach out to us. Here are our contact information. If you are, I'm based in Southeast Asia, so if you are from any region or any country from Southeast Asia, do feel free to reach out to me. You can also reach out to me on LinkedIn as well. If you are from India and Asia South, we have our colleagues Rohan and Debanjan. In Australia and New Zealand, we have Carl and Mike to assist you as well. If you don't know where to reach out to, no worries. Our e-store or our website has the chatbot. You can always reach out to us by submitting a question through our chatbot as well. And this session, if you require a recording of this session, we can also provide. You can also register here for us for a recording after this, so that you can watch it more easily. I'm going to share the link here as well. So feel free to register here so that you get the link sent directly to your inbox. And since there's no further questions from the floor, so thank you very much, Sington, for your time today. And thank you all of you as well for joining us today. We hope this session gives you good insights on the analysis of in open pit mining. So thank you so much. Have a good day, everyone. Take care.
Thank
Bye.
you. Thank you.
Thank
Bye.
you. Bye bye.